My name is Peter Larsen, and I'm here today to present to you the Overture VDM tools and the features we have in version 2.0. At the moment I have two projects included in my Explorer, a VDM-SL model and a VDM++ model, and I assume you know VDM already, so I'll just try to explain to you the functionality we have. Here we have an editor where we have highlighting of the different keywords in the syntax, and we have an ability to jump things in the outline we are seeing on the right hand side. In addition to syntax and type checking for these things, we can use a debugging functionality. Now I would like to show you how we can actually set a breakpoint, and we'll just try to put a breakpoint in generation, which is here, and then I'll go and use a debug configuration where I would like to call this Conway example with generations 130 and diehard. Conway Game of Life is an evolution of a population, and you'll see how it evolves over time. Now if I click debug here, it will start the debugger. It will go to the first breakpoint. I only put one in, and we can see where things were called from. We can see how the different variables are having different values at different points of time, and we are able to ask it to kind of go into things, step over it, or simply just resume. We're going back to the same breakpoint because we're actually having a recursive call here with an operation called generations. Now if we try to remove the breakpoint and continue, it will essentially give us a lock here at the end saying that the result of this is a sequence of sets, in this case 130 long, and the last one is going to be an empty set, meaning that this population has died out. This is not the most convenient way of seeing whether it actually does what you expect it to do. Therefore we also have the possibility of making graphical combinations of a VDM model. These are done by means of having operations that are defined as isn't yet specified. And for those ones we have also supplied a Java implementation in a jar file, and then if we try to call something similar to what we just did before, but just call the GUI graphic version of it, we'll see the evolution of it in a graphical manner. What you see here is simply the population, the evolvement of the population. We see the number of the round, and we see how they are dying out when we come to point 130. This is the way in which we can make it easy for people who are non-technical or non-VDM users to see what actually a model is doing. So it's an easy way to be able to present a model, which is essential from an industrial perspective, although this is a very toy-like example. You'll see now we're almost dead. We also have a possibility, when we've done things like this, to produce test coverage information, and we can get that out in a LaTeX document. In our generated folder here we have coverage information from the executions we have just carried out, and in here we can actually see online whether things are green, that means they've been covered, or red, they have not been covered. We can see exactly the same information in the PDF document we just produced by LaTeX. If we look down here, you will see some red parts. I'll make it bigger. Red parts which have not been covered, and black parts which have been covered, and then we automatically get tables like this one showing us how many times we've been calling an operation and to what extent the coverage is covering the entire operation or function. So these are the kind of things we can do with this functionality. Let's try for a moment to change over to VDM++, where I have a tree example, essentially modeling searching in trees. But here I'd like to show you a feature we have called combinatorial testing. Combinatorial testing is essentially a way of writing a regular expression that is going to expand into a group of test cases. Then those test cases we can then try to automatically execute. Now I just say full evaluation, and automatically it's going to execute it in 100 times, it looks like, and you can see some of them didn't find any violations of things, but some of them did find violations. So here we had a problem in a breadth first search. Let's try to go to that particular part, send it to the interpreter, and it goes to exactly the line we are interested in, and we can see we have a copy-paste problem. Left tree is empty, do this. If not, left tree is empty, go to the right tree. So if we fix this, save it again, go back to our combinatorial testing view and try to rerun our test, we will, after it's been executing these 100 test cases again, see that they are all green, meaning that they couldn't find any violations of things. Another thing we can do in order to kind of improve quality of things is we have something called proof obligation generation. If I can generate proof obligations like this, we have a number of cases where we need to ensure that we cannot get a runtime error. So here, for example, we have a case expression. There's no others clause written here, and therefore it needs to be exhaustive. So that's what this is saying, and this is the actual property that it should hold. It's for all things of case tree, it should either be empty or there should exist something in the tree where it's a node. These things we would like to take to a theorem prover. At the moment it's not built into the graphical GUI here, but we're working on that, so hopefully that's going to be in a future release. We hope to be able to show that to you later. Now, I'd also like to show you how I actually got these models in here. I simply used import, and then there's something called Overture and Overture examples, where I can now try to take a VDM real-time model, and instead of taking all of them, I'll just take one of them. This one is for countermeasures. It's a military application for missile being fired against you. Now let's look at the model here. We have different files. Among those files we have something that is used to indicate a system perspective, where we have a distribution between different CPUs, in this case 6 CPUs. We have 3 buses, and we have a number of things that are being deployed to those different events. The idea behind this is that we can simulate a distributed system. So if we go in here and try to do a debug. Now let's look at the debug configuration for this one, because I'd also like to show you that we have a possibility of doing different kinds of checks. Now this time I'm asking also to log real-time events, and we'll see what these real-time events can be used for afterwards. In this case I'm using some kind of scenario telling me when different missiles would be fired against me from what angles, and we're seeing here what is the reaction from the system based on that. You can imagine that a graphical animation of that could also be helpful. But what we also get in the generated thing here is a log, and this log file we can view graphically like this, where we see different CPUs, how they're connected to each other using buses. We can see an overview of the execution, where we see different, let's move a little bit in the time, we see the different CPUs, how they're communicating over buses, and we can see each individual CPU, how the different instances deployed to that CPU is communicating using different operations and connecting to the buses. So this is a convenient way to be able to see what's going on in these settings. Another thing that's worthwhile here to consider is that you have the possibility of writing validation conjectures over such traces, and those validation conjectures can be checked and graphically viewed in case you have things like this where it's violated. So I hope that this gave you an impression of some of the things we can do using this tool, and I hope that you would like to either use it, or in case you're interested in helping us further developing it, please contact us. Bye for now.